Hey guys, Mr. Smith here, and we're doing our fifth lesson of Unit 7, the last lesson in this unit. And we're going to take some of the things we've done with exponential and logarithmic equations, and we're going to apply them to a couple of scenarios. If you ever get into city planning covers such a wide variety of topics, and a lot of the things you have to plan for, like population growth, increases in traffic in a certain area, um, ecological things like populations of predator, prey, birds, insects, etc. A lot of things obey either exponential growth or decay or logarithmic growth. And the mathematics behind a lot of these things involves solving exponential and or logarithmic equations. So in this lesson, we're going to do a couple applications. We're going to model some data using an exponential function within Desmos. We're going to solve a few exponential and logarithmic equations, just diving into a bit more detail and trying to make our scenarios a bit more realistic. So let's go into our first example. So we have the town of Decimal Point, and it's been growing for several decades, and we've got the growth. So the time is the number of years since 1920 when the population reached 1,000. And then we see the growth every 5 years after that. Now, I know we've been recently working with exponential functions, logarithmic functions, and that population is clearly increasing, but there's lots of functions that increase. Linear functions can increase, quadratic functions can increase, exponential ones can increase. What is the best fit for this model? Well, I would argue from just the table itself, not really clear. Let's make a scatter plot to illustrate, and then we'll see maybe things will become a bit more clear. So I'm just going to write along with you guys. I'm going to be doing all this stuff from scratch within Desmos so we can all follow along. But yeah, let's head to Desmos, and we're going to first make a scatter plot. So we'll add a table, and I'm just going to keep things as x1 and y1, and I'm just going to kind of enter my data. So 0, 5, and then Desmos will go up by 5s for you. We're going up to 30, and I'll get our population entered in here: 1,100, 1,180, 1,250. Of course, you have the flexibility just to pause the YouTube video, do this on your own and catch up or what have you, and 1,600. All right. Of course, we can't see any of these points on our graph because our window right now is going from minus 10 to 10 and minus 7 to 7, roughly. So let's change our window settings. I'm going to change so everything kind of fits fairly well. Let's go from like minus 5 to 35 for the years. And then let's go from, how about negative? I want to get the the x-axis in there. How about negative 100 to 1,700? Okay. Gets our data fit in there. We can see it. Now, I would argue, so again, pause the video and make sure you've got the data entered. If you use a slightly different axis than settings than I did, that's okay. We should all have relatively the same graph here. Now, I don't know about you guys, but I'm looking at that data, that rough data, and even with the visual, I still really can't tell. Is that linear growth? Maybe it's swinging up a little bit. It's hard to tell. Is it linear? Is it quadratic? Is it exponential? We're still unsure. So what we're going to do is we're going to perform regression. Regression means fitting an equation or fitting a curve to some data. And you guys, depending on which classes you've taken, you'll have a variety of experiences with regression. Everybody in their grade 9 math courses did linear regression. It's like making a line of best fit. And depending on your course, your teacher, some of you guys maybe have even taken data management or taking it right now and may have got into this already. But we're going to perform some regressions at Desmos. Specifically, we're going to create a quadratic model and an exponential model. And we're going to see if one is a better fit than the other. So the way we do that in Desmos, and again, this if it's new for you, like pause it when you need to, slow down the playback, go back and forth, but just take the time and make sure you learn how to do this right. The way you perform a regression in Desmos, it's actually very slick. Back even 10 years ago, when I was earlier on teaching, we doing these things with graphing calculators, we'd spend more time training you guys how to use the graphing calculators and tracking down batteries and stuff than we actually did actually performing regressions. But you guys can perform regressions really quickly with tools like Desmos. So to do a quadratic regression, what we're going to do is we're going to type in y1 because we're going to make a function in terms of y, and y is our population values. But it's important to use y1 because we want to use those values in the table. We do the tilde, which is usually beside the 1 on your keyboard, a little squiggly. And then we're going to create a general quadratic equation here in standard form. So a and then ax squared, but instead of x, we have to use x1 again, so that we use the data in our table squared. And we need an x term plus b times x1 plus a constant c. And when you do that, just make sure you get it right. We should all have the same stuff because we're all going from the same data. You should see that Desmos has fitted a curve to your data. The curve is a parabola. We can only see a small snapshot of it right now. And it gives you those parameters, the A value, the B value, and the C value. So I'm going to just flip in back to our note there, and I'm just going to get this equation copied out. So the equation for our quadratic model was y equals, Desmos said our A value was about 0.15. Our B value was about 15.4. And our value of C about 1,006. One other thing that Desmos spits out, and other regression tools that spit out too, is under statistics, you'll see this value r squared equals 0.9967. If you take data management, or you've taken it already, and you might be getting into this unit if you're taking it right now, but this measure r squared is called the coefficient of determination for this regression. And it basically tells you how good your model fits the data. And r squared generally runs between 0 and 1. Well, it does run between 0 and 1. And the closer you are to 1, the better your curve fits the data. Now, in our question, we got an r squared value of 0.9967. Which is very close to 1. This curve fits our data very, very, very well. At the very least, it fits this small window of data extremely well. Let's try an exponential regression. So I'm going to flip down to a new spot here, and we're going to now perform an exponential regression. And so we do something similar, y1, to make sure we're using the data from our table, tilde, and then our exponential function is just going to be a simple one of the form a times b to the power of x. So parameter a, brackets, you can have b, power of, and I think, yeah, Desmos does that just fine. Close it off. And you can see we get parameters a, about 1,006, and the rate of exponential growth, b equals is 1.0157, so about 1.6% rate of population growth. And you can see that our two graphs almost indistinguishable. The r squared value for our exponential model is actually the same. So let's get that model down on our sheet. Let's get that coefficient of determination down. And then it looks like we need to talk further about which model would be a better fit. 1006 times 1.0. Zoom in a little bit here, actually. 1.016 to the power of x. And our coefficient of determination, 0.9967. Okay, so A through C we have now done within Desmos. And as we have talked about, R squared value, very similar. And these two graphs, within the data, almost indistinguishable. We can't really tell the difference between the two. But what if we zoomed out a little bit? Maybe that will give us more of an indication on which one of these might be a better fit for us. So I'm going to take my x values, and I'm going to just go back maybe 20-ish years, maybe go 20-ish years in the future. And then I'm going to just show, maybe go to 2500. Yeah, I think that shows pretty well. Might even go a bit farther in the future just to show. Go to 70, from 1920 to 70. Yeah, I'm pretty satisfied with how this looks. It gets at our talking points. So you guys can see that the data that are two curves within the data. So if you just focus on those points, right, the points that we were given from t equals 0 to t equals 30, both of the curves essentially the same, hard to tell the difference. But look towards the ends, right? For negative 20, which would be around the year 1900, you can start to see that the graphs kind of diverge a little bit. And you can start to see, too, that diverge a little bit as you move to more positive x values or as time increases. And what you're going to see is, because our black line here, or at least black on my computer, our first one, the quadratic one, because it's quadratic, that means at some point it's going to have a vertex. And that vertex, because this one's kind of concave up, it's opening upwards, that vertex is going to be somewhere in the past for you guys. And what this is going to mean is, at some point that in the past, the population was at a lowest point and it started to grow again, which meant it was at a lowest point and the population was actually higher and decreased, reached the lowest point and it increased again, which doesn't really model the scenario here where we said this function has been increasing in population for years and years. So you guys can see, as I just click and drag to the left here, you can see the exponential model is giving us predictions where the population is getting smaller and smaller and smaller, closer to 0, like exponential functions do. But this quadratic model, as we've seen, it reaches a minimum around 50 years before 1920, and then it's just going to keep increasing and increasing and increasing. And I would argue, and I hope you guys would agree as well, that doesn't really make sense given the context of the problem. So it's really not enough to just look at, hey, which curve fits my data exactly. A lot of curves can often predict with the data very well within the actual data points. But when it comes to extrapolating and predicting outside the data, you have to consider that when choosing a model. And hopefully that made sense to you guys. Our quadratic model isn't the best choice because it diverges and eventually is going to reach a minimum of our population, which doesn't make sense in the context of population growth. The exponential model is the one that we should be choosing. So for part D, I've left for you guys to kind of make your own point form, dot jot, whatever you want to discuss there. But we have landed on exponential as the best choice, and for all those reasons that we just discussed. I'll let you guys put those reasons there in your own words. Please feel free to pause the video if you want to kind of compose your thoughts. All right, let's continue. So part E. So now that we've established the exponential model is ideal to use, In terms of planning the city and planning growth, because if let's say that we infrastructure needs to be expanded when the population hits a certain amount. In Part E, we're talking about a recreation center, but this would apply for fire services, police services, libraries, schools, electricity, water, sewage, all kinds of stuff. So in this simplified scenario, we're decided that once we reach 5,000 population, a recreation center should be built. We need one for a population this size. That's not something you want to wait till you reach 5,000 and then start the process, because that process can take years and years to get permits, to get somebody contracted to do the construction, to actually perform the construction. You want to plan this ahead of time. So we want to plan, when will the population reach 5,000? So let's dive in here. Now that we have a model, and if recall that our model, you guys have this on your sheet, I'm going to rewrite it down. The model was 1006 times 1.016 to the power of x. And for our model, remember, y was the population and x was the years. The years since 1920. In this particular question, we're told, hey, the population is 5,000. Set y to be 5,000 and solve for x. And fortunately, you guys have been solving all kinds of exponential and logarithmic equations. In the grand scheme of things, this is not the hardest equation that you guys have solved, but it's a useful one because we're solving it in terms of the context of this problem here. So let's do it. Let's divide both sides by 1,016. And we'll just bring up my graph here so we can verify later. And we're going to want to keep some accuracy here. So I'm going to leave things as exact. We could do, to get 1.016 by itself, we're going to divide by 1006, but I'm not going to divide that and get a decimal. I'm just going to leave it as 5,000 over 1006. We'll let our calculator sort out the work later. All right, how do we get at that x? We have developed our tool. We can take the logarithm of each side. So the log of 5,000 over 1,006 is equal to x times the log of 1.0. You know what? I might show that in 2 steps there. I have more space. The log of 1.016 to the power of x. And again, we have our power rule for logarithms. So we can bring down the x. This is equal to x times the log of 1.016. And now we can get the value for x, our years. We'll take whatever the log of 5,000 divided by 1,006 is, and we'll divide that by the log of 1.016. And then once we get our value for the years, we can head to Desmos and just verify that this kind of checks out. So, all right, let's do it. Log of 5,000 divided by 1,006 divided by the log of 1.016. You should try it too. I got about 101, and again, that is the years since 1920. So we can make a little conclusion here. I'll tuck this in over to the side. Recreation center should be built. So 100 years since 1920, that would be 2021. Again, that's 101 years after 1920. So they best get digging. we can forgive this question. This question was made up certainly significantly in the past. See how it worked out to be this year. Well, assuming you're watching the video in 2021. Okay, so a really useful application of solving exponential functions. We modeled a set of data, some population growth, using regression, using an exponential function, and then we used our new skills for solving equations to make a prediction about when the population will reach a certain amount. And if we head to Desmos, when will the population reach 5,000? So that is our red model, I think. About 101 years. I think because we did some rounding. Yeah, we certainly did some rounding. We used 1.016 because the actual value is 1.01574. We actually overestimated the growth a little bit. And you can see 101 years, we're only at about 4,700. If we did our question using more accurate 1.01574, we probably would have got somewhere closer to 103 years, which would still be pretty close to what we got. All right, so Desmos kind of confirms, and hopefully, aside from the math here, that you guys now are a bit more clear on the difference between curve fitting and modeling. So our quadratic and exponential, remember how we just had a graph centered on the data? Both curves fit the data really well. In terms of curve fitting, they were both fantastic. In terms of modeling, one of them wasn't so good because the quadratic model predicted that the population in the past would actually start to go up again, which doesn't really fit. So when you're choosing a model, you definitely have to consider the context of the problem and think about how it extrapolates. What does it say in the past? What does it say in the future? In the next example, we're going to look at the compound interest formula. Now we're going to look at the math behind it. These days, like a mortgage broker or an investment analyst, somebody, a financial planner, is going to have a computer in front of them and just punch in these features into a computer, and the computer will do the math. But we want to be able to understand what's going on behind the scenes. And and again, you guys want to be able to choose the best mortgage, choose the best investment plan when you guys move on and get careers, et cetera, et cetera. So here we're going to look at an investment in two different investment plans and decide on an optimal strategy for us. So let's say we have $50,000 to invest to build our recreation center. We can invest that right now, so in the future we have that money to build our recreation center. So we have two options. We have the Lakeland Savings Bond, where we pay 6.25% compounded annually. That means the interest is calculated once a year, each year. But there is a condition. So if we withdraw the money before 10 years, we have to pay 2% of what we borrowed as a bit of a penalty. So a bit of an early withdrawal fee, very realistic in terms of a lot of savings accounts, et cetera, et cetera. Our second option is Northern Equity Mutual Fund. So we get a smaller interest rate overall. However, the interest is calculated more often. It's calculated semi-annually, which means twice per year. There are no conditions on this one for withdrawing our money early. We can withdraw our money wherever we want. And this is kind of realistic. There is a trade-off between these two things. You know, you can't have your cake and eat it too. You want the best interest rate. There might be conditions on it. So what we're going to do together is we're going to construct a model using the compound interest formula that you guys developed in your grade 11 course to look at how each investment will grow as a function of time. And then consider which one will be the best option, which option doubles our money faster, but then also considering that we might have to withdraw our money earlier, does that factor in? So let's get going. So if you guys recall the compound interest formula, A equals P times 1 plus psi to the power of n. Remember, A is the amount of an investment. You guys might have referred to that as future value in your grade 11 math course. The initial value, P, the principal, is often referred to the present value. It's how much you're either borrowing or investing. And one important thing, well, two important things in this compound interest formula, we have to understand that N is not always just the number of years. N is how many times interest is calculated. And I is not the annual interest rate, it's the interest rate per compounding period. Let's look at our example and just reinforce that. So we're going to make a model, A of t, that models the future value of our investments after t years. With the Lakeland Savings Bond, if we go back and just check that out, we are compounding annually. That means interest is calculated every year. That means in our compound interest formula, if t is years, the number of compounding periods is just equal to the number of years. So that's easy enough. The number of compounding periods is equal to the number of years. When we're compounding semi-annually, which means twice per year, the number of compounding periods is not going to be the number of years. It's more than that. It's twice every year. The number of compounding periods will be 2 times the number of years. And if it was monthly, it would be 12 times the number of years. It just depends on the context of your question. So why 2? It's because interest is compounded semi-annually. The interest rate per compounding period, so for the Lakeland Savings Bond, it's a little easier. It's the interest rate per year. So little I is just 6.25%, but we need to make sure we write that as a decimal. So I might write that in words first, actually. So the interest rate per compounding period, it's 6.25% compounded annually, which means that in our formula, we'll be using 0.0625, and that's it. Interest rate per year is the interest rate per compounding period. For our next guy, however, 6% compounded semi-annually. You guys can do the mental math. Well, that's 3% per half year. To get that numerically, we would take the interest rate for the whole year, 0.06 as a decimal, and divide that by 2. So 2 ways, one with mental math, it's 6% compounded semi-annually, 6% for the year, divide that by 2, 3% for half a year. In our compound interest formula, 3% per half year, 0.06 divided by 2. So now we can create a model for each. So for the Lakeland Savings Bond, we have that the future value is the initial value, which we know. In our case, it's 50,000. So let's plug that in. Our value for I is 0.0625. So 1 plus that is 1.0625. And the number of compounding periods is just the time in years. So we have a model. Perfect. And for the Northern Equity Mutual Fund, we have the same principle. We have a different value for I. So we have 1.03. And in the exponent, we have 2t, double the number of compounding periods. Now that we have a model for each, we can find the doubling time for each investment. So let's do that. I should have enough room on either side. So let's do, I'll just put LSB over here. So we're looking for when does the value, the future value, equal $100,000. That's the doubling. That would be 50,000 doubled. And we have to solve this equation for t. We get exactly 2 equals 1.0625 to the power of t. Those are awful t's, oh my goodness. And we're old hats at this now. We know, take the log of each side. I'll just take it slow and show this extra step. If you're already comfortable and you know that when you take the log of the right-hand side that the t is going to come down, I'm okay with doing that in one step. I'm just showing that I'm applying our rule. Then we can get t by itself. T equals log 2 divided by the log 1.0625. How long does this investment take to double? Log 2 divided by log 2 divided by log 1.0625. So it looks like about 11.4 years is what I got. And then for our second guy, the Northern Equity Mutual Fund, we're doing a similar process. 100,000 equals 50,000 times 1.03 to the power of t. Now, arguably, it's the same steps. It's just we're replacing 1.06 with 1.6, 1. Well, we're replacing 1.0625 with 1.003. I need my 2 there. So again, if you can cut down on the steps, like that's okay. I'm going to show all the steps just to be safe here. You do notice in this question, the small difference is that in the exponent we have 2t, but our strategy is still the same. Take the log of each side, 1.03 to the power of 2t. Use our power law of logarithms, bring the 2t down, 2t times the log of 1.03. And then we get t by itself. We get the log of 2 divided by 2 times the log of 1.03. And let's see if this doubling time is the same, less, more. Let's find out. Log 2 divided by 2, log 1.03. So about 11.7 years. All right. Now that doesn't necessarily make one investment better than the other in terms of purely how long it takes to grow. Yeah, the first one takes longer to grow. But again, remember, there was a penalty for withdrawing early. So let's continue on here because we're going to be looking for when we're going to have $80,000. And obviously that's less than 100,000. So that's going to be less than 11.7 years. And if it's before 10 years, remember, even though the Lakeland savings bond grows faster, before 10 years, like it's going to be worth more, but there's going to be a penalty for withdrawing that early. So that's something to keep in mind. Let's graph both of these functions that we created in Desmos. So I'm actually just going to refresh Desmos and get a fresh palette to start from. Reload. Let's punch in our 2 functions first, and then afterwards we can change the window size to see them grow. So I'm just going to put in y equals, so it was $50,000. And our first was 1.0625. The power of t, I'll just use x here. And clearly we don't see that function because it's way off our screen, right? And our second guy is y equals 50,000 times 1.03, the exponent, and then just make sure we get 2x all in the exponent. Yep, 2x all in the exponent. I'm going to change my settings. I'm going to go from my x-axis from -1 up into maybe 15 because it reached 100,000, both of them between 11 and 12 years. That should give me a spot to see that. And then let's go, how about -10,000 up until 120,000. That shows everything pretty clear. And you can see that, initially they're growing virtually the same rate, but then you can just see the Lakeland savings bond. It's doubling a little bit faster. You can see it kind of breaking away. And you can see that So we've done part C. We've kind of graphed both of those. We can see the Lakeland savings bond diverging a bit. But we need to. We're gonna withdraw this money once we have $80,000. So let me add a third function here, 80,000, and you can see that they each reach $80,000 just around 8 years. And what we, even though we get $80,000 quicker with the Lakeland savings bond, we're going to be penalized for withdrawing early. And is that penalty for withdrawing early going to make it a worse option than the mutual fund? Well, let's actually add in another option here. So I'm going to make a new function. It's going to be the same as the original Lakeland savings bond. However, I'm going to add this. We're going to graph this one as if we got penalized for making a withdrawal. Remember, the penalty for making a withdrawal was 2% of the principal? Well, 2% of the principal, 2% of 50,000 is $1,000. I believe, I just did that on my calculator. I believe you can make Desmos calculate this. And you can see we got a new graph there that just shifted the original one down by a little bit. And so now we can make an apt comparison with the penalization. And now at this point, I am going to zoom in for both. With the penalty, I'm zooming in here. They both, that's quite too far zooming in. It looks like it's very similar. They both, after 8 years, if you consider the penalty, both of them basically give the same amount. It's almost a toss-up, and it looks like financially it wouldn't really matter which one you pick. That you may have to consider other factors too. But let's actually, now that we've seen it's roughly after 8 years, let's actually look at that from an equation standpoint. So we graphed both investments in Desmos. We added a third graph when the penalty applies, and we were able to compare. And we saw that we should get 8 years. So yeah, let's check out part D. How soon can the work begin? Which investment option should be chosen? Graphically, it looked like there's a tie, and it looked like after about 8 years. Let's verify that using our equations. Just split my screen down the middle here. So let's dive in. So let's do the Lakeland savings bond here, and we have to. This is important. We have to actually tie in. I'm using Y. We're using A. We had 50,000 times 1.0625 to the power of t. But remember, with the penalty, since we're taking it out before, and graphically we saw this, we know it's before 10 years, we have to account for the penalty. And we're setting A equal to 80,000. And we're going to solve for t. 50,000, 1.0625 to the power of t. Very similar to what we did earlier. You just now have this extra step of adding 1,000 to each side. And of course, for the other guy, the mutual fund, Northern Equity Mutual Fund, there is no penalty for this guy. 1.03 to the power of 2t. And we're setting this one equal to 80,000 and seeing when it reaches. Again, visually, we already know both about, that is missing a lot of stuff. We know that we're going to get close to t equals 8. Maybe visually we just estimated a bit off. Maybe there is a bit of a difference. But can you guys solve these two equations? We have the tools. If you want to pause the video and give that a try, I would highly advise that. If you want to follow along with me, that's okay too. But please, I would encourage you, if you don't like listening to me drone on and on, pause the video, try it yourself, and then you can just fast forward and check your answer afterwards. All right. So I'll keep a little bit more accuracy here. So 81,000 divided by 50,000, get that by itself. I'm not going to divide that in round. I'm just going to keep everything accurate. Equals 1.0625 to the power of t. Now I might, just to save some space here, keep things a bit simple. So log of 81,000 over 50,000, and maybe that's equivalent to 81 over 50, just to make things easier on my calculator. And I know when I do the log of the right-hand side, I'm going to get t times the log of 1.0625. So how long is it going to take? Well, whatever the log of 87 over 50 is, divided by the log of 1.0625. All right. I guess dividing by 50,000 actually would give you a decent enough decimal. It's not too crazy. Well, actually, it's an exact decimal, 1.62, I think. But we're already doing this. It's all good. So the log of 87 divided by 50 divided by the log of 1.0625. All right. That's 81. What did I should erase that. Because I got 9. I was like, oh, our graph said 8, and I think our graph's pretty accurate. Let's try that one more time. Okay. I got like 7.96 years. So very close to 8 years. So, if that was our only investment option, including the penalty, basically 8 years, we could withdraw 50,000, we'd have 80,000, and we can start construction. So solving our guy on the left, we divide both sides by 50,000. Now this actually just gives us, I'm not going to write 8 over 5. That actually just gives us 1.6. So let me write 1.6 here. 1.03 to the power of 2t. Again, I think we've done enough of these. Hopefully we're okay. If I take the log of 1.03 to the power of 2t, I know the 2t comes down. And I can solve for t. I get the log of 1.6 divided by 2 times the log of 1.03. We're expecting close to 8 years. Yeah, I got 7.95. So the conclusion is work can begin after 8 years. And financially, there's not much of a difference between the investment options. For this particular context, right? If I was saving like for 200,000 in the future, clearly the Lakeside Savings Bond, we showed that long term with no penalty, it's growing faster. But for this particular problem, it wouldn't matter which one we invest with. But and there might be other things to consider. Okay, so what would I expect you guys to do after this lesson? I'd expect you guys, if I give you a set of data, I'd expect you to be able to perform a regression, a quadratic or an exponential, and compare the two. And explain why. We talked about the difference between curve fitting and modeling. Explain why, in this case, an exponential model was better than the quadratic, even though they had the same R-squared values. So again, know the difference between curve fitting and modeling. And once you come up with a model, you'll be able to do the things we do with our exponential functions. Plug in a value of x, find a value of y. Given a value of y, find a value of x. I also would expect you guys, given an investment scenario, to be able to build a model using the compound interest formula. We did 2 examples here, and then play around with those in terms of some context. Here we compared to investment options. All right, so I've got some suggested practice for you guys. As usual, this wraps up Unit 7, and we just got one more to go. All right, hope you guys enjoyed that lesson. I enjoyed giving it for sure. Hope you guys are staying well. Take care. We'll see you soon.